Okay. Yeah, we will talk about the versatility of ICP analysis in earth science focused, and it's kind of like an introduction we're going to give you today.
Okay, so yeah, a bit of a brief introduction as to who we are and what we do. I'm Sam Hammond. I have a background in geochemistry, particularly igneous geochemistry. So I did a PhD a number of years ago now, looking at lithium and lithium isotopes in subduction zones. And then I went on and did a postdoc for a couple of years looking at trace element composition of meteorites, in particular carbonaceous chondrites. And since then, really, I've been working as a sort of laboratory technician or as a laboratory manager, and really specializing in ICP-MS analysis, in solution ICP-MS. So I started using a single quad instrument about 17 years ago when my tech career began. And for the last 10 years, we've been using a triple quadrupole ICP-MS here at the Open University.
Yeah, and I'm Barbara Kunz. I'm from my background a metamorphic petrologist and geochemist, and I specialize in laser ICP-MS analysis. I did my PhD many years ago in zircon geochronology, and since then I focus more on trace element analysis in a range of geological materials. And overall, by now, I think I have over 16 years of experience and have worked in different labs. And since I think about 8 years or something, I'm here at the Open University and work with Sam. So we share a lab, and I'm kind of like her, a bit of like a lab technician, lab manager, and we work together.
And yeah, so our lab, as you probably know, we're at the Open University. We have a triple quadrupole ICP-MS, and we're going to explain what that does to you today. We use it for measuring trace element concentrations, and some selected isotope ratios is something we're moving into doing in the last sort of couple of years. And we use both a solution introduction and a laser ablation system that we've got as well. And we mostly focus on the analysis of geological and environmental materials or environmental samples. And we work with students and academics that are here at the Open University, but we also do quite a bit of work with visiting collaborators who come to use our lab to do work with us. So that's sort of the setup as to our lab. That button. And so I guess a bit of an outline as to what we want to talk to you today. This is really intended as an introduction and an overview, and it's incredibly brief. We could talk for days about this sort of stuff. And obviously you're not here for days, so we won't be doing that. But this is really a brief overview of what the instruments can do and how they do it, what sort of things you can potentially analyze, and crucially for you, what you should be considering to be able to get great data out of these kinds of instruments. So we're going to start by looking at the instruments themselves. We're going to introduce ICP, so the inductively coupled plasma, to you. And then we're going to think about some of the different types of ICP instruments. So I guess the different back ends that we can stick onto the ICP front end of the instruments that we're looking at. And then we're going to think about the strength and versatility specifically of the quadrupole ICP-MS, because that's where our expertise lies. And we're going to talk about both the solution and the laser ablation kind of introduction systems and the benefits and disadvantages of both of those. The second part of the talk, we're really going to think about sort of analytical strategy, and this, relates to quadrupole ICP-MS, but also goes much deeper into other analytical techniques that you might be using. So thinking about how you can get the best data from your samples. So thinking about sample preparation, about different calibration strategies, the effects of matrix matching, the effects of fractionation in the plasma, things that you can do to ensure quality control, a little bit about data processing, and then at the end we are going to leave hopefully some time for questions. If there's anything that you think of outside of this that you would like a little bit of clarification on, then do feel free to contact us. We should be relatively searchable, and you've got the address of our lab in the presentation. So yeah, go back to look at the recording and you can track us down and ask us questions if you need to. So we're going to start at the beginning and work through from sample introduction through to the plasma and ionization. So thinking about sample introduction, I've said that we can either introduce solutions or solid material into our ICP machines, and we can either digest our solid material to turn it into a solution, or we can directly ablate that solid material. So solutions are taken up via a peristaltic pump and fed into a nebulizer. And so there's an image here of the nebulizer, so you can see our sample is taken in through here. And there's a series of gas flows, carrier gas that feeds the sample through the nebulizer and creates this fine mist. The mist then enters the spray chamber. And so the larger droplets fall through the spray chamber and out towards the drain, and the finer droplets make it through towards the torch to the plasma to be ionized. The spray chamber can be horizontal or vertical in its orientation. It really depends on the flavor of ICP that you have, but the principles are very similar. And sometimes spray chambers can be cooled. So the spray chamber that we have on our quadrupole ICP-MS is a cooled spray chamber, which just means that we get more effective condensation of the droplets that form, which means we get a narrower range in size distribution of those droplets that make it through into the plasma. So yeah, as I said, the solid material can either be digested and fed in as a solution, or it can be directly analyzed via a laser ablation by bombarding the sample surface with a laser beam. So the sample is placed into the laser ablation chamber and ablated by the laser. And the interaction of the laser on the surface of the material creates a plume of material. And that plume is then carried into the plasma to be ionized from the laser ablation into the ICP itself. And we usually use helium as a gas to do that because it's relatively light and allows for good transmission of that particulate material.
So we spoke a bit already about like the plasma and it is part of the name. So ICP is inductively coupled plasma. What is a plasma? So a plasma is a state of matter, a bit like solid and liquid and gas form. And we use this in order to ionize our particles that come from either the laser or the nebulizer. And typically we use an argon plasma, and I think most ICP instruments do use argon plasmas, although you can get microwave plasmas which use nitrogen, and there are also potentially other gases that you can use. And they all have advantages or disadvantages, and the argon one is kind of like, I guess, kind of like an alternative of or compromise of the best and also affordable, because argon isn't too expensive like other noble gases. And on top of here, you can see this is like an image of the plasma in our instrument, and it comes kind of like here out of the torch onto the cones that then goes into the instrument part here. And down here, because you can't see much on the top image here because it sits behind the cage to shield it, is a schematic image of the torch, which is basically kind of like several concentric glass tubes, although glass it is a quartz. And you can see that gas gets introduced through different ways, and this, the carrier gas, which contains our sample, either solution or laser, is injected into the middle and surrounded by other gas flows. And then here you can see in white here the RF coil, which is kind of like where a spark is created, which excites the argon, and the excitement of the argon is what creates the plasma. And then in the plasma, you ionize the particles that we want to analyze, and there are several processes that happening within the plasma that kind of like break apart our molecules into individual atoms and then into ions. And it's important to note that only part of the sample gets ionized, so not all sample is turned into ions. And we can adjust the plasma characteristics, and we'll come to that a bit later throughout the talk in several points again. So why do we need to ionize particles? So first of all, it is then possible to separate the ionized particles in the mass spectrometer. This is why we need ions. And we ionize by basically losing an electron because we are interested in positive ions. You can see on here, and this is kind of like a bit basic chemistry, that you need a certain amount of energy in order to remove an electron from the shell of the atom. And that energy depends on kind of like how many shells do you have, and how close the electron is to the nucleus of the atom. And the closer the electron is to the nucleus, the harder it is to remove it, and the more energy is needed. And therefore, you have a decrease of the energy that is needed down each group because you add more shells, and so you're further away. And you can see this here, like in each of the groups across the periodic table, is that you need kind of like the energy changes kind of like across the mass, and it increases across a period as well. This is then kind of like, because we want to analyze mass to charge ratios. So it's important to consider the mass as well as the charge of the ions. And as I already mentioned, kind of like we optimize the plasma, and there are several ways of doing that. And we try to we optimize the plasma to have elements ionized which have a high first ionization potential, but reduce the formation of doubly charged ions, because we don't want to have those, because they could create interferences which then kind of like cause problems with our measurements. And overall, it is important to consider to not overload the plasma, because if you add too much material to the plasma, you also kind of like inhibit the creation of ions. And then it's worth noting that the distribution of temperature is uneven throughout the plasma. So it's hottest in the centers. This is the ideal place where we want to kind of like, where we can create ions the best. And this is the part that we want to introduce into the mass spectrometer. And we kind of like can optimize this area that we sample by changing the gas flow, the position of where the torch sits within the instrument, as well as the RF power. And here on the picture, you can see kind of like a bit how different energies and gas flows kind of like create different plasma conditions, and then how that is affected here on the side if you then introduce a solution into it.
So we've introduced the sort of the ICP side of things, the inductively coupled plasma. So going from our solid or our solution into the constituent ions of that sample or standard that we're introducing. But there are various different things that we can do now once our ions are kind of separated. Now we've generated those ions in the plasma. How can we separate and detect those ions, which is ultimately what we want to be doing? So there are two main ways of doing this. We can do this by optical emission, looking at the wavelengths of light that are emitted as the sample is kind of introduced into the rest of the detector, or we can separate by mass. So I'm briefly going to talk about the way that we can separate using the wavelength of light that can be emitted from an ion beam. Talking about the ICP-OES, and the reason I'm talking about this is because they quite often appear in earth science departments. They're quite widely used, and they're really good because they can measure from sort of part per billion concentrations up to 8% concentrations in the samples that we're looking at, depending on the dilution and the different elements that you're looking at. So they're a bit of a workhorse, really. They also tend to be quite good at measuring those lighter masses, where mass spectrometers tend to struggle a bit because of the interferences from different gases that are introduced, either argon or oxide or nitrogen or things like that. So they have their advantages. So what happens in the ICP-OES is that we're measuring wavelengths of light. So different elements have characteristic wavelengths that they emit. And the light is separated through an assortment of different mirrors and diffraction and ordering and grids. And the ultimate production is this oscillogram, which you can see over on the left-hand side here. So this is kind of like the output that you get from an ICP-OES. And this is basically an organized visualization of the light wavelengths. And so each of these different pixels relates to a different element, and you can see that sometimes we get clustering of these pixels, which indicates that there's some potential interference on the elements that we might be looking at. And the brightness of these peaks indicates basically the concentration. So the brighter it is, the more of that element that there is in this sample. And so these oscillograms can then be transformed into peak responses based around target wavelengths, which then allow us to calibrate calibrate the data that we're getting, and leads us to being able to characterize the concentration of different elements in the samples that we're looking at. The second way of separating is by mass, and there are various different ways that we can separate by mass as well. So separation by mass is basically measuring a mass to charge ratio, and the separation is based on different principles. So there are different principles of mass separation, which lead to a variety of different instrument types, and all of these have advantages and disadvantages. And again, this is another thing that you could spend days talking about. So this is really, 30 seconds of something that could be several hours worth. But the three main types that we have are the magnetic sector field, time of flight, and quadrupole instruments. So in a magnetic sector field, charged particles are deflected in a magnetic field. And so these charged particles then follow a curved flight path, and the lighter ions are deflected more. So that means that there's one mass in the center of the flight path, and this can be detected using a single collector style of instrument, or if you've got a multi-collector, then you can collect several of those dispersed masses simultaneously. So these are really good for high precision measurements because you're detecting those masses simultaneously. Disadvantages of a magnetic sector field is that the magnet stability is such that it takes a long time to switch between extreme kind of mass variations. The next kind of instrument is time of flight. So this is quite a fast acquisition. So we introduce ions and they're accelerated in an electric field. And the heavier ions basically take longer to reach the detector, so take longer to travel a fixed distance than the lighter ions. These have advantages in that you get a full mass spectrum every time, but the disadvantage is that they have a limited sensitivity. And then, because this is our area of expertise, the focus of the rest of the talk is on a quadrupole ICP-MS. So moving charged particles in a quad are mass filtered in an electrostatic field. So this has advantages and disadvantages we're going to talk about. So because of the way that the magnet works, we can cycle through the masses very quickly, but these instruments are generally less precise than the magnetic sector field instruments.
Yeah, so as Sam already mentioned, we will focus on a quadrupole, and here's kind of like the inside and the outside of a quadrupole instrument. And this is kind of like our old instrument here on the side that is by now, I think, 20 years old and is still
25.
25. All right. It's 25 years old and it could still run. We don't run it very often anymore because obviously technology has evolved a bit and it's not as sensitive. But they are kind of very robust instruments and versatile. And if you take well care of them, they can last you a long, long time. So they're kind of like a good investment in some ways. And as Sam already said, they do the mass separation using a quadrupole. And we'll get to that in a bit to explain kind of like just very generally how that works. And they typically have a single detector, and we'll get to that as well. And the modern instrument have a whole range of add-ons such as collision cells, collision reaction cells, a second quadrupole, or various ion deflectors, and all of them kind of like help the mass separation. So as I said, the quadrupole is the mass filter in a quadrupole instrument. And it's kind of like 4 parallel rods that have a DC and an RF voltage applied to them, creating the electrostatic field. And the focused ion beam will pass through the middle. And only ions of a particularly mass to charge will be resonant in that electrostatic field and will pass through to the detector. And all other ions will simply kind of like collide with the metal rods and don't go through to the detector. And by varying the voltage, we can then kind of like allow different masses to go through to the detector. And modern instrument can kind of like scan of more than 10,000 atomic mass units per second, which allows us to completely scan the mass range more than 30 times per second. And compared to TOF instrument, as Sam already said a bit, that we only at one point target one mass, which means we need to select the masses that we do want to analyze, and that the mass resolution is less than a magnetic sector field. However, we do have a big advantage that we have this large dynamic range that we can scan across, and the sensitivity advantage compared to a TOF.
Okay, so yeah, why all the Qs? So yeah, 25 years ago, the example that we showed in that picture, the instrument that we had the plasma, had a series of lenses, had then just the quadrupole, and then the detector. But as time has gone on, you see that various different instrument manufacturers are advertising all of these different things. There's triple quads, there's 4 Qs are better than 3, all of this sort of stuff. And some of this is actually really a misnomer. A triple quad isn't really a triple quad. It's 2 quadrupoles. And in between those 2 quadrupoles, there is a collision reaction cell, sometimes called an octopole reaction cell in the center there. 4 Qs again, it's a kind of a lens at the beginning between, and then there's the 2 quadrupoles, and then there's the collision reaction cell in the middle. But why do we need these quadrupoles? Well, the key is that they're really good for interference removal. So when we're ionizing stuff in the plasma, we're breaking apart individual ions, but we're also creating kind of different species in that plasma as well. So we have the ability to be able to create interferences that overlap on the masses that we're particularly interested in looking at. And if we have an overlap or from an imposter element or an imposter kind of species, then that means that the actual amount that we're measuring is not true. We're measuring more than we should be on that particular mass. So there are lots of different types of interference that we can consider. So we can consider isobaric interferences. So that's a different element on the same mass. For example, argon 40 is the same mass, will interfere on calcium 40. We can overcome that by measuring calcium on a different mass, for example. We can create doubly charged species. So that's because if our ionization is too efficient and we're stripping away more electrons, we form doubly charged species. So for example, cerium on mass 140, doubly charged, has the same mass to charge ratio as germanium on mass 70. We can create polyatomic species, so a whole host of things here: oxides, argides, chlorides, hydrides, nitrides if we were introducing our sample in nitric acid, and these can all have an effect. And then there's also tailing effects that we need to consider as well. So argon has a huge peak because that's the majority of the plasma. There's not very much else in there, and these tailing effects can sort of overlap onto the adjacent masses. So potassium on mass 39, for example, has a huge tailing effect from argon. So the formation of some of these interferences can be reduced with good tuning, but where this isn't possible, in the past we would have had to have done chemistry to try and separate out these interferences. But that has problems if you want to be looking at laser ablation, where doing wet chemistry is not possible to your sample. So can we use these quadrupoles and the collision reaction cells to help us to try and eliminate these interferences? So what follows now is a little bit of a discussion about collision and reaction cells, but also a little bit of a potted history of ICP-MS instruments as well. As I said, you can use careful mass selection to try and remove interferences, but if this isn't possible, then previously we would have had to have done separation chemistry. But as instruments evolved, instrument manufacturers thought about ways of being able to do this separation by using technology in the instruments rather than having to do chemistry. So the first step that they made was to insert a collision cell. And on the very first instruments, this collision cell was placed after the plasma and the first set of lenses, but before the quadrupole. So the collision cell works by having a cell and inserting an inert gas into that cell. And as you pass your sample through it, it transitions through this cell. But if you've got polyatomic species that you've got in your sample mix, they're more likely to collide with the gas in the collision cell as they are bigger. And when they collide, they lose their energy. And if we apply a voltage barrier to this cell, then those bigger particles that have collided won't make it through the cell. And therefore, this diagram's a bit the wrong way around. But if we've got our mix of analytes and polyatomic species here, we've got collisions with our polyatomic species in the cell, whereas our analyte is more likely to make it through. And then our analyte makes it through to the detector, whereas applying this energy barrier means that the polyatomic species don't make it through. And this is referred to as kinetic energy discrimination. So it used to be that that was kind of at the front end before the quadrupole. In multi-quad instruments, this sits between the quadrupoles. So and now it's not just a collision cell, but it's a collision and reaction cell. So the reaction cell is a really neat way of trying to remove interferences. So in the early days, again, the reaction cell was just before the only quad in the instrument, and it used reaction chemistry in order to try and remove or reduce the interference. But the advantage of the so-called triple quad is that we have a quadrupole before the cell, Q1, let's call it, before the cell, so we can control what masses go into the cell. So we've got a much tighter constraint on the chemistry that's happening in that reaction cell. And then we can set Q2, our second quadrupole, which then leads to the detector. So we have two modes of using our reaction cell. We can either do what we call an en masse or a mass shift mode with regards to the reaction. So there are a couple of examples here from our lab, things that we routinely use. So the top example is an en masse reaction here. So something that we're interested in measuring is silver in volcanic samples. Now this is generally sort of tens of parts per billion concentration in the samples that we're analyzing. But this is measured on mass 107, and this has a problem because it has a zirconium oxide interference. And zirconium is typically in the hundreds of parts per million concentration in the samples that we're looking at. So even with relatively small oxide production, even if it's about 0.5%, we're still getting a significant contribution of counts on mass 107 that are coming from zirconium oxide. So what we do, we set our first quad to be mass 107. In the cell, we use ammonia because the zirconium reacts really readily with the ammonia and forms a different species which doesn't have the mass of 107. But the silver doesn't react, and therefore we set our second quadrupole to mass 107, and just the silver then transitions through the quad and into the detector. The second example is mass shifting. So an example of what we do in our lab here is using oxygen in the cell and measuring selenium. Again, selenium is in very low concentrations in the samples that we're measuring, and it suffers from a whole host of interferences that you can see here that have the same mass to charge ratio as the selenium that we're looking at. But selenium forms a very exothermic reaction with oxygen. So it means that in the presence of oxygen, the reaction is incredibly likely to proceed, whereas the analytes, this reaction is not going to proceed. So what we do is we actually shift the mass of our second quadrupole to 96, which is the mass of selenium at 80 plus the mass of oxygen at 16. So we set that at 96, and we're effectively measuring selenium oxide on our detector. So advantages of the reaction cell are that we can avoid separation chemistry, and it has a whole host of applications, particularly looking at laser ablation and moving into the possibilities of isotopic analysis by laser ablation. The disadvantages are that all of these Qs cost money, so these are more costly than the single quad instruments. We do have the potential to form unwanted species if we're not careful with the chemistry that we do. So you have to do quite a bit of investigative research before you're happy that this is going to work. And there is the potential to lose some sensitivity as well. So you do have to monitor all of these things before you're happy that you can proceed with this work. And if we just want to do regular analyses like we would have done on our old instrument 25 years ago, we can simply just switch off Q1 and the cell, and we can just use Q2 as our mass filter and detect things in no gas mode. So we have the ability to do that if we need to.
So yeah, onto kind of like the last part of the instrument, the detector, and we mentioned this already a couple of times. And we also mentioned that quadrupole instruments generally have only one detector, but actually they have one detector that contains two pods. And why it's only one detector is because they don't operate at the same time, but they operate depending on kind of like the concentration that we're analyzing. So the first one is kind of like is the electron multiplier or the pulse detector, which is there to kind of like analyze low signals. And it works in that the ion beam like hits the dynode and emits an electron when the ion beam hits it, and that kind of like then slams into it another ion and kind of like multiplies in that way, and exponentially like amplifies the signal. And the other type of detector is the Faraday cup or the analog detector, which where an electron flows through the detector, and in order to neutralize it, the ion, we create a current, and that current is measurable. And those detectors are very simple and robust, but have slightly lower sensitivity compared to the pulse detector. And so, depending on kind of like what concentration your element is, either the pulse or the analog detector will analyze it, but they won't do it at the same time. However, in multi-collector element instruments, you have either several Faraday caps or electron multipliers sitting next to each other. But the advantage of the triple quad is that we have both detector types within one detector, and therefore it allows us to measure a large dynamic range of nearly 11 orders of magnitude in terms of concentration, which makes them a very versatile instrument. So after having discussed all of the different parts, this is kind of like how it looks in reality. So these are the kind of like two instruments that we have in our lab. Here you can see, and they're mostly just kind of like gray or white boxes, where you can't see a lot in it. On the left side here, we have our laser ablation system that we can couple to the ICP-MS that sits here, our triple quad. Or we can introduce samples via the solution, where we have here kind of like the spray chamber and the nebulizer and our auto sampler. And because we are at the Open University, which is kind of like famous for its long distance learning, a couple of years ago, we together with a researcher have developed a virtual laser ICP-MS, which kind of like allows you to tune and analyze some things and train a bit and learn more about laser ICP-MS. So if you're interested in that, it's free to visit. So, what elements can we analyze? Any element that can form a positive ion in the plasma is possible to analyze, which kind of like covers therefore the majority of the periodic table, which you can see here highlighted in the different colors is a rough concentration estimate that you are able to analyze based in solution. However, this kind of like also depends a lot, as I said, on concentration, but also your background and potential interferences that Sam covered earlier, as well as it depends a bit on kind of like the amount of material you have. So a solution analysis always has more material compared to a laser ablation analysis, and therefore kind of like the concentration that you are able to analyze for each element as a minimum varies.
So moving on from what elements can be analysed, what kinds of materials can be analysed, and as I've said, we have a very earth science kind of focus in our lab, and I'm not going to dwell on this for too long because we've got more important things to talk about, and I'm mindful of the time. But we can look at all kinds of materials. So we can look at waters, soils. We can think about more geological materials. So we can look at silicates or carbonates, doing whole rock analyses. We can do mineral analysis for research and exploration. We can do volcanic monitoring, looking at melt inclusions and other constituents of volcanic samples. We can look at geochronology, so using the samples that we have for dating the formation of samples. Looking at paleontological samples, we can do paleo-environment reconstructions from looking at microfossils, so work on foraminifers. We do some work on biogeochemistry, so thinking about tracing pollutants or looking at bioavailable nutrients in samples, for example. And these are just some of the examples that we have in the field of earth sciences. There are lots of applications outside of earth sciences, so thinking about biological tissues, about chemical experiments, nanotechnologies, pharmaceutical applications, material characterization, and much, much more. So why would we want to use solution ICP-MS? So this is the only option if we have an aqueous sample, but if not, then we can take our solid sample and digest it. And if we do that, it gives us a bulk measurement of a homogenized solution. The analysis that we do is usually not time limited. We have plenty of sample. A couple of milliliters of liquid is enough for us to measure a lot of elements. I think 4 milliliters is enough for us to be able to measure over 60 elements in 4 different gas modes. So yeah, we can get through a lot of material using a solution ICP-MS measurement, and we can use multiple different collision or reaction cell setups in order to completely remove any interferences that might be hampering us. We've got access to a well-characterized set of matrix-matched calibration standards in terms of the silicate, the work that we do, some basaltic torolytic reference materials. But we can also create our own custom blends by mixing single element stock solutions to create blends that replicate the samples that we're looking at. In solution, it's relatively easy to monitor and correct for instrumental drift because we can bleed in an internal standard at the same time as introducing our samples or our standards. And it gives us a high precision measurement. So for the majority of elements, precision is better than 2%. Disadvantages of solution ICP-MS is that it does involve more sample preparation and digestion. You need access to a clean laboratory, clean acids, and that kind of thing in order to be able to do your digestion. If you're using digesting silicate rocks, you need to be able to have access to hydrofluoric acid, for example. I mean, it is a bulk measurement, which means that we lose a lot of the details of within sample variability.
So on the other hand, why use laser ICP-MS? And I guess the main reason is that the disadvantage that Sam just kind of like mentioned is that if you're interested in situ analysis, where it allows you to spatially resolve zones of a mineral or zones of a glass or fossil or any kind of material. And basically, we can analyze anything that is solid, including ice. These days, the instrument manufacturers have created cryocells, so you can basically directly ablate ice. And the dynamic range for element concentrations that you can analyze ranges from major element to trace elements and allows you also isotope ratios, so covers like the whole range. And this is because we have quite low backgrounds and low limits of detections, which allows us to analyze them. The external analytical precision depends a bit on kind of like what type of instrument you have. Usually for a single collector, you're around like 1%, whereas a multi-collector allows you to a precision of 0.01%. And you can have a very high sample throughput of like more than 200 spots a day. But I think even these days, it can go up to the thousands. And therefore is often kind of like said, oh, you can get very easily quick data. And I always say like it's possible to get quick numbers, but quick data is a bit of a false false promise here because in order to kind of like do the data reduction and check your data and understand it and make interpretations, that still takes a lot of time. And people, when they come to me in the lab and we analyze spots, they are usually kind of like overwhelmed by the amount of data they get just from a single day. So it's something kind of like, while it's quick, it doesn't mean that it's quick data. It's just quick numbers. So the question is like, how and why did you decide to use one instrument or the other? And it all depends on the research question and the sample material that we kind of like alluded to a bit. And there are a couple of points that we would like to highlight to think a bit about is kind of like if about the representativeness of your sample. So do you want to kind of like have a bulk measurement, as Sam mentioned, or do you need to have individual parts of your sample be analyzed? How much sample do you have, and how good do you need to be your reproducibility? Obviously, there are points to think about contamination, either. And that can be in both ways, in both solution and in laser, it can create that. The question is like, do you want to have a mineralogical or chemical characterization? So that's kind of like the spatial context in situ versus bulk. What accuracy and precision do you need? And then I think one thing that we often kind of like forget, but the availability of an instrument as well as the budget obviously is also a thing that kind of like plays a role when thinking about this. So this was kind of like a bit of the first part, and now we move a bit into the second part of the talk and talk a bit about analytical strategies. And basically that is, for me, I always say like that's the difference between getting numbers versus meaningful geological data. And there's a whole host of things to kind of like consider. And we'll just kind of like, again, like it's a whistle stop tour because we could like spend probably hours talking about each of these things. And we just kind of like want to highlight some of them. And we will cover this both in solution and laser ablation mode, sometimes next to each other and sometimes on separate slides. But a lot of this applies even not just to quadrupole ICP-MS as we spoke about, but are generally good things to consider for any kind of analytical measurements that you do. So first of all, sample preparation is the first step. Here, kind of like, obviously the solution side of things is a bit more involved than laser ICP-MS thing side, but you need to consider if you have a solid sample for dissolution, and you need to use the appropriate chemistry in order to do that. And then you have to dilute your sample. If it's a liquid, you might have to filter it, dilute it, or acidify it. For all of this work, the level of cleanness and preciseness is really important to get good data. And if you kind of like hurry through this and don't take care here, it doesn't matter how good your instrument is, you will never get kind of like good data. So we always like stress that this is really like an important step. And actually, you even have to take care already when you take your sample, but that we won't cover that today. But it's just a whole other thing to consider. For the laser ICP-MS, documentation is really important, because if you want to have the spatial context, you need to make sure that you do know what you analyze and not just randomly place laser spots across all of your sample. Either kind of like doing some SEM work or some thin section work on the microscope is really important in order to pick and really choose the areas of your samples that you want to target. And you need to prepare your sample surface either by exposing it, like an example up here in like some zircon grains, or down here in some melt inclusions. You need to expose it, and then you need to polish it. And an additional step is that you need to characterize an internal standard element. We'll come to that in a bit. So that's typically like a major element or a stoichiometric element. But if it's a major element, you need to analyze that for things kind of like by electron microprobe. And a second part to sample preparation is the risk of contamination. And theoretically, any step you can take, you can contaminate your sample. But some of the examples we just kind of like wanted to highlight a bit that we came across is in our work here is that down here you can see a plot. A few years ago, we've been giving samples to analyze basalts as powders. And we analyzed them, and you can see that you have like much more than an order of magnitude higher tungsten values than in most of the samples. And it took us quite a while, because it was only a few samples who were affected, to figure out that actually some of the material has been milled in a tungsten carbide mill. So obviously kind of like a lot of tungsten has been introduced, and they're not outliers or not a tungsten kind of like milling. And we had similar other things where we had silver analysis suddenly of 10 ppm, which is kind of like you would like start a silver mine if you have that kind of concentrations, because usually it's about 30 ppb. So we figured out after quite a bit of while that some of the samples have been crushed in a jaw crusher, and some of the metal bits that the rocks kind of like chipped off of the jaw crusher have been incorporated into our powder. And these kind of like things can happen, and sometimes they're obvious and sometimes they're not obvious, and sometimes you just have to painfully learn that you have contaminated your sample afterwards. And this is just kind of like to like show some examples and to make you aware of that whatever you do with your samples, you have to consider the potential for contamination. And obviously there's also things like user errors, that you like use the pipette tip in multiple samples and cross-contaminate things, or you close the wrong beaker lid and things like that. So care needs to be taken when doing the sample preparation. And on the laser ICP-MS side, you mainly have problems with coating, polishing material, or embedding materials. So if you've been to the SIMS and your sample has been gold coated, you have a lot of gold everywhere, and it goes everywhere, and it's hard to get rid of. Or if you've embedded your material in indium mounts for SIMS analysis, you will never do an indium analysis and in that material or you can, but it's very tricky. And the same thing is true if you use a polishing plate that contains metal and you want to analyze lead isotopes afterwards, you might contaminate one. And because you don't really know it and you don't know to which extent, it's really tricky then to kind of like figure out. So it's important to consider the sample preparation that is according to minimize the contamination risk for your samples.
So after you've hopefully prepared your samples in a clean and appropriate way, the next things to kind of consider are your instrument settings and your parameters. So after you've introduced your sample into the well, throughout the entire process really, the instrument needs to be tuned in order to get the best out of it. So tuning is needed at the start of each analytical session that you're doing. And we can tune to enhance sensitivity across the mass range that we're interested in. So if that's the entire periodic table, then from lithium right the way through to uranium. If you're just measuring the rare earth elements, for example, then from lanthanum through to lutetium. We can tune to reduce the interferences, as I've mentioned, so we can reduce the formation of doubly charged and oxide species. And we have elements in our tuning solution that mean that we can monitor how effectively these species are produced. And we can tune as well to get our backgrounds down as low as possible so we get the best signal to noise ratio. We can tune gas flows within the nebulizer and in the torch, and we can tune our torch position to ensure that as much of our sample as possible makes it into the lenses and the vacuum system of the ICP-MS. And then we have a series of electronic lenses before the quadrupole, which means that we can really focus the ion beam so that it makes it into the center of the quadrupole itself. Because if that is off center, then those voltages that we're applying across the quadrupole rods mean that the beam won't transition all the way through the quadrupole to the detector. We can change and tune parameters within the collision cell as well. So when I was talking about the collision cell, I said that selenium, for example, reacted with oxygen because it's an exothermic reaction. But if we give more potential across that collision cell, it means that we can start to introduce reactions in more endothermic reactions. So we can kind of push the limits of those reactions by altering the potential difference across the cell. And then, of course, we can tune the quadrupole settings and the detectors in order to get the best out of our instrument. If we are using the laser, then there's parameters that we can tune on the laser in order to be able to get the best out of the instrument as well. So things like the gas flow, the helium that we're putting into the laser ablation cell, and then other laser parameters can be changed and altered in order to get the best ablation out of the material you're using. So going into things like the laser repetition rate, the laser fluence, and all of that sort of stuff, which again affects how the laser interacts with the sample surface and how that particulate matter is then carried into the torch before it's ionized. Once we've done our tuning, the next thing that we need to think about is calibration. Why do we need to calibrate? Well, the detectors detect an electronic signal, counts per second or a current intensity, but we need to convert that to a concentration, as that's what we're actually interested in measuring when we're using our quadrupole ICP-MSs. So we use either synthetic blends or well-characterized reference materials in the case of our sort of basaltic to rhyolitic reference standards that we can use of a known concentration. And we run these at the beginning of a sample analysis. And so we know the concentration of these, and so we can create a calibration graph for each element that we're looking at, where we draw a line between the counts per second and the concentration. And then the counts per second that we get for our unknowns can then be converted into a concentration. If the concentration of the samples transitions the pulse to analog shift in our detector, then our calibration needs to cover this shift too. So the alignment of the pulse to analog modes in the ICP is not linear. There's a correction that needs to be applied between the pulse and the analog modes to get this linear detection array. And so we need to make sure that we're covering that transition if our samples are. So as I've said, yeah, we get our calibration lines by measuring reference materials with known concentrations. And these are either synthetic blends that we can create of solutions or synthetic solids in the case of the laser ablation, looking at synthetic glasses, or well-characterized materials with similar matrices to the samples that we're analyzing. And we're going to talk about matrix matching in a second as well. And the calibration range needs to be appropriate for the level seen in the unknown. So the two little schematics that we've got here on the right hand side can see that if you're calibrating just down the low end, but our actual unknowns are up here, the uncertainty in the measurement of our unknowns is amplified because our calibration is not appropriate. Similarly, the reverse is true if our calibration is well up here at the top end of the concentration, but we're actually measuring right down at low concentrations, then our calibration isn't appropriate here either, and we can introduce more uncertainty from our measurements because of the inappropriate nature of the calibration. Sometimes calibrating can be a bit of an iterative process. If you really don't know what it is that you're looking at, sometimes you have to go in, do an initial pass, think about where your unknowns sit in relation to the calibration. And it might be that you have to rerun with a different calibration that then more appropriately fits the range of the unknowns that you've got. So this is just a little example of calibration using the solution. And these are some real examples from our ICP-MS software. We have an adjuvant, so that software is called Mass Hunter. And you can see here we've got examples for barium at the top and nickel down the bottom. And what's neat here is that this software shows us whether the instrument is using the pulse or the analog detector. So the pulse detector measurements are shown in blue here, and the analog detector measurements are shown in green. And you can see that it's applying the factor that it needs to between the pulse and the analog modes very nicely here. And we're getting a nice linear array between the pulse and the analog detectors. The example of nickel down here, you can see that there's a pulse detector down here, analog up here, and this pink dot is actually, it's measured, so we usually measure each mass 5 or 7 times. So for some of these measurements, it's decided to use the pulse detector, and some it's decided to use the analog detector. So it shows these up as pink. So calibration curves are drawn for every mass measured at the start of each analytical session. We run our calibration standards and do our calibration from here. The pulse to analog factor is determined by the solutions that span that transition. The gradient of the line is applied to the unknowns. And in solution, matrix matching is usually straightforward. We either have reference materials of a similar matrix to our unknowns that we can use, or we can make up these synthetic blends, as I've said. We can bleed in an internal standard online as well to monitor and correct for instrument drift. So we can do that, and that helps us to ascertain whether our matrix matching is good enough or not.
So for the laser ICP-MS, this works principally the same, but the details are a bit different. So instead of analyzing our standards at the beginning of each analytical session, we kind of like use an approach which is called standard bracketing. Which means that we analyze some standards followed by our unknowns, followed by some more standards, and so on and so forth. And so you bracket your unknowns by standards. And it is also important to choose reference materials of an appropriate concentrations for your unknowns. However, this is quite challenging because we can't just kind of like dilute our samples or our unknowns appropriately because it's all of a solid. So sometimes we have to make a bit more compromises here than on the solution side of things. And one of the big challenges is matrix matching, which we will talk a bit more in detail, but it is important to mention this kind of like for the calibration as well, because this means that we always use the assumption that our knowns and our reference material and our unknowns behave the same. But if they have different matrices, that means that they behave optically and mechanically different during the laser ablation process, and therefore kind of like would introduce a bias. And to kind of like overcome this or partially overcome this, we often use an external standard, which is synthetic glass. And then to matrix correct, we use an internal standard, or there are kind of like also approaches to use bleed in kind of like synthetic isotope spikes. And they're kind of like, I could talk about this a long while, but I just kind of like would like to point out that there are like some really good articles that have gone into the depth of the different advantages and disadvantages of the different calibration methods.
So yeah, a little bit about matrix matching because we've spoken about this briefly on the last few slides. So as Barbara said, we make the assumption that both our calibration standards and our unknowns behave in the same way in the plasma in terms of ionization and in terms of ablation in the case of the laser ablation. So what we've done here is a little experiment where we're looking here at the recovery rate of our internal standard. So our internal standard is bled in online and is mixed in a T-piece before the peristaltic pump and the nebulizer. And it should remain constant throughout the run. So that's bled in at the same time as our blanks, our calibration standards, or our unknowns. So this should remain as a nice flat line. So our internal standard has got a range of different masses in it, from beryllium at mass 9 through to bismuth at mass 209, and they're represented by different colours on this graph here. And what we've got here is the percentage recovery of the internal standard, where 100% is basically the value at the very first analysis in the very first thing that we analyse. So what we did here is we introduced our internal standard, and then also bled in I guess samples of different matrix composition. So in the blue, you can see that we've got a matrix which is just a 2% nitric matrix here. And you can see that we have a relatively steady recovery of all of our internal standard at around 100%. The next thing that we did, because we've worked on some samples that contain this kind of sample matrix, is we introduced a matrix which was water with 1% IPA in it. And you can see that this has a significant effect on the way that the internal standard behaves. Well, in fact, every element behaves when it enters the plasma. So the IPA has the effect of enhancing the ionization of the sample when it's in the plasma. And you can see that there's a jump here of some 20% in terms of the ionization of the sample in the plasma. So if we were to use calibration standards that had just a nitric matrix, and then our samples had an IPA matrix, you can see we would get this offset that would mean that we'd be falsely reporting what we have in our unknowns. We then went back to our nitric acid just to check that we could return to our sort of steady state. And then we introduced a sample with a 0.1% rock matrix. So you can see that introducing rock matrix actually loads the plasma more heavily, and that actually suppresses ionization. So for the majority, apart from for some reason, apart from the rare earth, the thulium internal standard, you can see that we get suppression of all of the different masses in the internal standard because of the introduction of more material into the plasma, which means that the ionization is not as effective. So it's really critical that our standards and our unknowns do behave in the same way, and that we can monitor for that, and that we make sure that our calibration is as appropriate as possible. So as I've said, in solution analyses, we have the luxury of being able to create the same matrix for our standards as our unknowns. And we have the luxury also of being able to bleed in the internal standard to monitor for this online. But in laser ablation, this is more difficult, and so over to Barbara again.
Yeah, so we have quite a wide variety of matrices because we have different minerals which have different compositions and different optical properties, therefore. And it has been kind of like shown, and there's a whole lot of literature about this, that they do behave different during the ablation process, and therefore a different amount of material is kind of like delivered to the ICP. There is kind of like, now obviously, ideally we would have a standard for every of our unknown materials, but it is quite challenging to find reference material that is sufficiently homogeneous for what we're interested in, that is abundant, so that we can distribute it across all labs, so all labs can use the same standards, as well as is characterized and matrix matched. And this is even more challenging kind of like when we think about that a lot of minerals are solid solutions. So therefore we would then need different kind of reference material for different parts of the solid solution of a mineral. So this doesn't kind of like really work, and we often kind of like use an approach where we do a matrix correction, and this is particularly important for isotope ratio measurements, where already small differences can create a lot of difference in our results. And there often we try to aim to do matrix matching, but when that isn't possible, we often kind of like use a primary standard that isn't matrix matched but is well characterized, and then use a secondary standard that is matrix matched in order to correct this. And you can see here kind of like an example from the group in Adelaide who looked at rubidium strontium geochronology. And you can see in pink here, they used a NIST 6 10 glass, so that's a synthetic glass, to do their standardization of their mica unknowns. And then they have used two different kind of like micas. To do the secondary matrix correction, and you can see that you get a difference depending on which one you use. And I don't want to go into the details here, and this is just kind of like to illustrate that the matrix that you use, the matrix your standard has that you then apply to your unknowns does make a difference in terms of your calibration. And this kind of like leads us on to kind of like next topic of fractionation, because some of this kind of like of the different behavior of the matrix is also kind of like something to consider. And for laser ablation, there's the laser-induced elemental fractionation, which kind of like causes differences in terms of how elements are transported and reach the ICP-MS. But it's also important to say that not just during the laser ablation you can fractionate, you can also fractionate in the plasma, although this is kind of like a bit less well studied. And ideally, you want to minimize both effects in order to get good data. Here you can see some examples of two. Of kind of like how does the fractionation look like during laser ablation. And you can see that different laser energies, as well as a different duration of your signal, kind of like cause different patterns for the same element. So you can see the mass range from light masses to heavy masses here. And this kind of like is related to some of the element properties. And down here, you can see a different graph that kind of like, again, shows that across a period as well as across the groups of the periodic table, you do have a different different laser fractionation patterns, which has something to do, again, with the property, the chemical or physical properties of the elements. And you generally like try to find laser ablation as well as plasma conditions that minimize these effects.
Okay, so if you've made it through all of these hurdles, the next thing that you need to consider is your data processing. So these are largely similar between the solution and the laser, but let's go through these individually. So in terms of solution, data processing, it's important that you check your chemistry. So for example, look at your blanks, your chemistry blanks, and make sure that your chemistry blank isn't contributing any counts to the unknowns that you're looking at. You need to apply your calibration, remove unknowns that fall outside of this, and go back to reanalyze those with more appropriate calibrations if needs be. You need to correct for instrumental effects, so drift over time. If you are introducing samples with a fair amount of matrix, so rock samples, a 0.1% rock matrix, then you are going to get build up over time on your cones, and that will limit the sensitivity of the instrument over time. So you do need to correct for that. And then we can also run monitor block where we have a standard and an unknown in that monitor block. So we can check for precision by the reproducibility of a monitor run throughout the analytical period. And we can check for accuracy by looking at the variation between a processed reference material and published values or long-term data. In terms of the laser, the data processing involves selecting the part of the signal to be used. So this is effectively doing the chemistry, if you like. So selecting the part of the signal, because the laser produces a time resolved analysis, it means that over time the laser might drill down, for example, into a different mineral phase. It might pick up an inclusion within the mineral that you're looking at. You might actually make it through the mineral into the glass slide. So you need to select the portion of the signal that you're interested in. You then apply your calibration, as Barbara has already described, and you can also correct for instrumental effects drift, again, because we're using a consistent kind of monitor analyses throughout the course of the analytical session. You can check for the accuracy using a secondary standard, check for that against the published values. And data processing for solution is, in my experience, largely done with the package that's provided by the instrument manufacturer. So we use our Agilent package that's produced in terms of the solution data processing. For laser ablation, this is a little bit different. Lots of the ICP manufacturers are getting better at including laser ablation kind of information, but this has largely not been the case. And so there are a whole range of programs out there that you can use to process your laser data. And these different programs all have advantages and disadvantages depending on which ones you pick. What's really important when you're processing your data is that you pay attention to any high backgrounds or blanks and try and work out why that might be. Pay attention to sample or signal outliers, and then any systematic or unsystematic instrument effects and what that means for your actual your numbers. Once you've processed your data, then you need to assess the quality of the data that you're looking at. So we should always be running certified reference materials if they're available, or sometimes just called standards. And the reason that we're doing this is to ensure that what we're doing is good and that we can replicate the same numbers as somebody else in a different laboratory. We want to be looking at our chemistry and our instrument blanks. These need to be as low as possible because we want to make sure that what we're measuring is actually in the sample and it isn't a contribution from sloppy chemistry or from dirty reagents, for example. We need to look at whether our instrument has drifted, looking at our monitors that are run throughout the session, and we need to correct for that if drift is a significant factor. In terms of looking at data quality, it's great if you can look at doing repeated or duplicate analyses or duplicate sampling as well in order to make sure that consistency applies throughout your analysis. Documentation is key. Barbara spoke at the beginning about documentation is incredibly important for the laser ablation in terms of making sure that you're hitting the exact right spots in the minerals, but also in terms of the solution work, making sure that you're documenting what you're doing and making sure that you have got all of this sort of properly documented is really important when it comes to, publishing this data that you're looking at. Sometimes it's important, or it's possible to do a cross instrument or cross lab comparison. So we've done some work, for example, looking at particular samples or standards that we've run on our ICP-MS and our ICP-OES and checking that for the same elements we're getting the same values, but also checking between labs, so looking at different standards that you pass between different laboratories who have the same instrument to make sure there isn't any instrument biases there that you need to be aware of. So these things, whilst they apply to ICP-MS, they also apply to other techniques as well. So there's a great database that I'm sure many of you are aware of, the GRM database, which has been catalogued by the Max Planck Institute in Mainz. But this is a great place to go to look at published and preferred values for a whole host of different reference materials. So do go and look at that if you're not aware of it yet. But I would also caution to be aware of the quality of data that's been published. So, as time moves on, as we're more aware of different interferences, as technology evolves and advances, then some of the original published data might actually include values that at the time were considered to be correct, but now that we can go and investigate further, we might think that there's some potential interference there. So if you think that's the case, then you need to do a bit more investigation, go back and do a little bit more kind of chemistry using, I don't know, like doped solutions to try and work out whether there are interferences on the masses that you're looking at and what that could potentially mean. So just to summarize really what a good analytical setup looks like. You should be doing tuning every day at the beginning of your analytical sessions. You should be running reference materials that are appropriate for your samples, ideally concentration and matrix matched, although this, as we've said, can be difficult for laser ablation analyses, and there are ways to try and overcome this. We should be measuring blanks. We should be looking at chemistry blanks, and we should be looking at instrument blanks throughout the run to make sure that the instrument isn't getting dirtier throughout the run that we're doing. We should be looking at using monitors that are run throughout the analytical session or looking at secondary standards. Ideally, it's great if you can start with your lower concentrated samples and move to the more highly concentrated samples later on in your analytical session to make sure that there isn't any kind of instrument carryover, although you can monitor for this by running sort of nitric acid samples throughout the sample run. Sometimes it's better to run multiple batches rather than to compromise on your analytical settings and just fitting it into one particular run. So it might be that you want to run several different gas modes, or you want to run a gas mode in several different ways. So, for example, if you've got some an element that reacts very exothermically with oxygen, therefore you don't need a potential across your cell, and then you might want to run that same gas reaction cell, but with a different voltage across the cell to try and persuade more elements to react. So it might be better to do that as multiple batches rather than just one analytical batch. And if you can, of course, choose an isotope mass that has no or minimal interferences. But as we've said, that really isn't always possible, and so you need to think about, how you do that with regards to the collision and the reaction cell. So some generalized analytical setups, sort of analytical lists in our lab, and I guess the differences between the solution and the laser side of things here. So in solution, as I've said, we run our calibration standards at the beginning. So this is a typical setup for a silicate rock setup that we would have. So here's a range of certified reference materials that we would run at the beginning. And these are digested in the same way and at the same time as our unknowns. We then have a monitor block that we run throughout the analytical session, every sort of 5 or so unknowns. And in that monitor block, we're typically running a certified reference material, a sample unknown, and a 2% nitric. So we do this to help us to monitor and correct for the drift, to make sure that we can look at the reproducibility of the certified reference material, and also we can average this and then look at the accuracy of that certified reference material. At the beginning of our unknowns, before the instrument has the potential to get sort of too dirty, we'd run our chemistry blank or our total procedural blank, and then we're into our unknowns that are separated by these monitor blocks. In terms of the laser ablation, because that wealth of calibration standards isn't available, the setup looks slightly different. So we run some primary standards and then secondary standards throughout. So these are used for our calibration, and then the secondary standards are used to check our data quality. Then a selection of up to 20 kind of unknowns before we then move back into our primary standards, our secondary standards, and then onto more unknowns before we finish off our analysis with more primary and secondary standards. And we do this, to help us for calibration, but also to help us to monitor and correct for drift throughout a laser ablation run as well.
Yeah, so we already alluded to that documentation and note keeping is really important. And how this looks, this is just an example of some of my lab books, but you can do this digitally as well. But it's really important through every step, throughout the chemistry, throughout the analysis, to make notes, because if you get data that isn't quite what you expected, you want to understand, is this real, or is this something that didn't work quite out? At whatever stage you want to investigate that. And some of the things that that I typically write down, and it depends on what your analysis is, but it's always good to write down some kind of your instrument settings, as well as which day it was. I always, if I do laser work, do a sketch, just to know in which part of the cell was it. And then I write down information about the standards, the unknowns. I do some comments during the analysis or during the data reduction, depending on how I run the samples. And this everyone does it slightly different, but it's really important to record it, and also to record, if you do chemistry already during the chemistry, oh, that sample looked a bit weird. I don't know, it was totally black, or this was very transparent, or there was something in it, or things like that. It's really important to record, and a lot of people these days, because a lot of software does save certain things, so you can go back to your file and you can get which day it was. Then people start to forget to write down all of these additional things, but they're really important in order to understand data and in order to make sense of them. So although things have moved maybe on from paper old school, it is still important to document everything. And that is also important then for data reporting. This is not just important for a publication, but also important throughout your working with your data, that you have very clear structured tables that have a header which they contain, and that you know which column it is, because I have to admit that I have spreadsheets where I have done some quick calculations and I have no idea what column H is anymore because I have not written down what it is, and it's something. And that's really frustrating because it just you have to redo things, or you kind of like lose information. Um, and then kind of like more for the publication side of things, it's important that you make use of captions as well as footnotes to explain things and to make readers aware and understand what you have done and what is in your table. And it's also very important to kind of like tabulate only significant digits. So if your precision is 1%, and you have four digits after the decimal place, that's not very helpful because it looks way more precise than your analysis actually are. So you would kind of like cut this down to maybe one. So it's important to consider. Obviously, if you have none and you kind of like look at 0.00 something, then that's not really helpful either. So it's to choose the appropriate ones. And on top of kind of like reporting as well as documenting, it's also important to document analytical conditions and metadata. And this is an example from Matt Holstwood, who kind of like made some recommendations of what you should report. In this case, it's for laser ICP-MS analysis, but the same is true for solution analysis. And there are very many good examples out there in the literature to kind of like what write down for what analysis. And this is simply so that people can understand how did you get to the data, and maybe they want to recreate or reproduce some of the data, and then they should use similar settings, obviously, because it might have slight differences or explain slight differences. And if you're kind of like looking forward to set up a new method, this is always a good place to start. So Sam and I are huge fans of analytical metadata, because that kind of like allows us to kind of like, as a starting point, to evolve methods or to adapt methods that are new to our lab.
So yeah, just the last couple of slides, just briefly mention some of the applications that we've been doing in our lab. So we've been looking at high precision accuracy analyses of chalcophile elements by using the triple quadrupole. So that's looking at elements like silver, which have been particularly difficult for us to be able to measure. Looking at complex matrices and chalcophile elements using the triple quad. So this is looking at those IPA water mixes that we've been that I was talking about, that have been used to extract volcanic aerosols from filter papers. We can look at low sample, low volume analysis. So, for example, the work that we do on microfossils, where we can get down to between 3 to 15 individual forams for a trace element analysis, where we look at trace element ratios in terms of reconstructing paleoclimate. Or looking at the meteorite work that we've done, where we digest between 3 to 5 milligrams of material, because that is obviously sample limited for the amount of meteorite that we're given in order to do the digestion and the bulk chemistry on those. We've been doing some trace element mapping using our laser ablation system, an example of which you can see up here. And we are moving into using quadrupole to measure the rubidium strontium system in various geological materials using the triple quadrupole as well. So this is a PhD project that's a year in to its progress now by Igor. So yeah, this is details about his PhD project that we're trying to move into now.
Yeah, and kind of like one other application that like shows a bit more also the potential that we use for the laser ICP-MS is that we've done like the bulk rock analysis of high precision and accuracy analysis of chalcophile elements, but we then also wanted to move and complement this with melt inclusions, which creates quite a bit of a challenge because you're very sample limited in terms of the melt inclusions are small, and then they have kind of like bubbles or they have inclusions or other material. And I spent a lot of time trying to get this working, where we actually kind of like, instead of a spot, we use a line scan, and where we scan across the melt inclusion. And you can see the signal here, where we actually kind of like, usually we try to avoid any kind of mixing between different materials. But here we kind of like accepted a bit of mixing material to then order to get a small bit of clean material that we kind of like then allow us to choose this part of the signal during the data reduction. So we get a clean melt inclusion signal. And then we have been able to analyze in melt inclusions kind of like sub ppm levels of selenium and arsenic. So that's kind of like really pushing the limits of what we thought was possible. And with this kind of like we've talked enough, I think, kind of like and hopefully haven't completely overwhelmed you, but given you like an overview of like the versatility of ICP instruments, as well as kind of like showing you kind of like why they're powerful tools to analyze trace elements and isotopes in geological material. We talked a bit about like strategies for kind of like why to choose certain instruments, and that it all depends a bit on your research question, and that diligence and care is necessary to produce high quality data that are the backbone of any kind of like research publication, and that all of these factors that we kind of like cover like feed into the data. And with this, we kind of like would like to thank you for your attention and have some time for questions now.
Thank you so much. That was genuinely brilliant, so detailed. That was absolutely excellent. Thank you. I feel like I learned quite a lot, even though I've done quite a lot of ICP and laser, but I felt like this is a good refresher. So we have a few minutes left just for questions, because I know people need to get away. But of course, as you say, your contact details were there and people can get in touch afterwards, or we can put people in touch if needs be.
Yeah.
Pankaj, would you like to ask your question, or I can read it out?
Yeah, hello. I'm audible? Yeah.
Yes.
Yeah, actually, I have run the ICP-MS to collect the rare earth elements data, and yeah, mostly I'm working on the rare earth elements. So I have used the standards which contains rare earth elements as well thorium and the uranium. But for the like lanthanum, I have got very high concentrations, while the all the rest of the rare earth elements was quite appropriate. So, like, what should be my approach? Should I reduce the dilutions, or is there any way to work on
Do you mean that the lanthanum in your unknowns is much higher than the rest, or
Yeah, yeah, yeah.
so
Lanthanum in the
it
yeah,
sits above the calibration? Is that what you're?
yeah, like compared to the CRMs, like when we compared with the CRMs, do we check the precision, and that was above 15%, while rest of the elements was very good, 5%, 4%.
Yeah. So I mean, so if your unknowns are above the calibration, then that's something you might want to
Yeah.
consider
Mm.
changing the dilution. But if it is that your reference materials are producing numbers that are too high, off the top of my head, I'm not sure why that would be for lanthanum.
Okay.
But yeah.
Yeah, I think it kind of like it's it can be lots of factors, and I think it is maybe worth to kind of like see that that if you use a slightly different dilution factor, do you get the same result? So it's in some ways, anytime you have any problem with these like analytical things, it's always kind of like working your way through different possibilities, and often it's like sometimes there's an easy answer, but a lot of times it's just simply like systematically working your way through it. Like, can you exclude that it's a dilution factor problem? Can you exclude that it's an instrument problem? Can you exclude that you have an interference? So kind of like, look, like, can you maybe analyze something that is, do you have a standard that is only lanthanum? So do you can reproduce that one so that you have nothing else in there? And so you need to like work your way through all of the possibilities, because often there's not one answer, or there is one answer, but you don't know the answer immediately. And so it's kind of like starting different approaches to that. Does that make sense?
Yeah, yeah. So I have to work with the dilution basically. Yeah, yeah. Or
Yeah,
yeah.
start there, and then and kind of like look at other
And then
influencing
CRMs,
factors.
yeah. Thank you.
You're welcome.
That's great. Are there any other questions? You don't have to type it in. Oh, yeah, we've got a couple. You're welcome to call them out yourself, or I can.
Let's have a look. I have a few questions. How many times the CRM should be repeated during analysis? So I assume because you're asking about downhole fractionation that this is about laser. Is that correct? Yeah, so kind of like how many times it depends. That's a good question. And again, I think there's not a simple answer. So kind of like if we, for example, in our lab, if we analyze trace elements for minerals or basaltic glasses, we usually kind of like run, as you saw in the presentation, we run 2 of our primary reference materials and 2 of our secondary reference materials, and we run about 10 to 20 unknowns, and then we run the standards again. And if you want to have more spots, we will kind of like repeat that pattern over and over and over and over again until the end. However, like when I did zircon geochronology, for example, because it was an isotope ratio analysis I was interested in, and I wanted to have it much more precise, I analyzed actually 3 or 4 primary standards at the beginning of my block, and then the unknowns, and then a secondary standard. So that kind of like varies a bit, and it also depends on kind of like how reliable is your primary standard. If your primary standard is very precise and well characterized, 2 is probably enough. But if they are a bit heterogeneous, then it might be that you actually analyze 3 or 4 times in order to cover that heterogeneity of your reference material that you then apply. And the downhole fractionation correction, yeah, I mean, I could probably talk equally as long as we have just done together about laser ICP-MS, and maybe this needs to be a different course in the future. We'll see. That yes, downhole fractionation is something that needs to be considered, and a lot of data reduction programs have algorithms that take care of that process. They kind of like look at the downhole fractionation of the reference material and then apply that to your unknowns. Again, with the assumption that you have a similar behavior, which is a whole can of worms that I don't open right now. But if you have kind of like more detailed questions on that, like, please feel free to get in touch and we'll try to cover it or answer it. But there are also kind of like lots of publications around all of what we mentioned that go into the specific details of it. I hope that covers that question.
Brilliant, thank you. If there are, oh yeah, great, okay, perfect. That's just a thank you there. If there aren't any other questions, I guess the only thing I would request from you is if there's any specific literature, we can link things on our MinSoc webpage. If there's anything, you can always just drop me an email afterwards if you think, oh, these 2 papers really do cover anything, or your own publications, of course, as well. But I think with that, if there are no more questions, we will end it there. Thank you both so much. That was genuinely so interesting. I really, really enjoyed that. And just really appreciate your time and the effort, because I know how much goes into these, and that these are just a fantastic resource to have online. They get really well accessed, and you really then capture a really, really wide audience. So just to say thank you again. For those yeah, you can contact them through the OU website. I'll pop that in the chat for you. The only thing is that if you have any questions, please feel free to contact me or Kevin. We can put you in touch, and I think we will call it there. So thanks very much, everyone.
Yeah, thanks a lot. It was our pleasure.